I'm taking a look at problem 4 in section 4.9. This is a related rates problem. It tells me the kinetic energy equation relating mass and velocity. In this case, the relationship is kinetic energy is half the mass times the velocity squared. Tells me that a spaceship's fired in orbit. Tells me that the kinetic energy is increasing at a constant rate of 100,000 units per second. Mass is decreasing at 20 kilograms per second because of rockets consuming fuel. I want to know the rate that the velocity is changing when its mass is 5,000 kilograms and it's traveling at 10 kilometers per second. In this case, the equation pretty much takes care of everything as far as needing to draw a diagram goes. So the important thing here is I need to figure out what my variables are going to represent. So, of course, I have my original equation there. That's important to know what I'm dealing with, and we'll talk a little bit more about that in a second. Looking through here, the kinetic energy is increasing at a rate of 100,000 units per second. That's the change in the kinetic energy. So that is going to be a value of dk dt is equal to 100,000, and I'll annoy every science teacher in the world by leaving out the units for the time being, but we will go back and look at that at the end. Going back to look at the problem again, it says that the mass is decreasing, and that's important to keep in mind the sign there. Mass is decreasing at 20 kilograms per second. So that's dm dt, the rate of increase of the mass. And again, that is 20 kilograms per second. Going back to the problem again, at what rate is the velocity changing? Okay, so the rate of change that I'm looking for, that's a dv dt that I'm looking for, and it's important to know that. Notice that I have three different derivative values here. So when I take my derivative, interestingly enough, I'm not going to need to replace any of these variables. I'm going to have to use all of these, which is going to make that derivative a little bit more challenging, but we have those values as they currently stand. Let's go back here. Let's see, it says what rate is it changing when the mass is 500 kilograms and it's traveling at 10 kilometers per second. Again, the mass is changing, so that 500 kilograms is going to be a mass value. M is 5,000 kilograms. However, I can't substitute that into the equation to replace a variable. Again, keep in mind I need a dk dt, a dm dt, and a dv dt, so I'm not going to be able to take out a variable. And it says that it's traveling at 10 kilometers per second. That is a velocity. And let's see, I think everything is in seconds and kilograms. I don't need to do any unit conversions here. Okay, so I think I can convert over here. The big thing is I need to take my derivative, and my derivative is going to be with respect to time. So derivative of k, of course, is 1 times the derivative of the inside function. That's going to be 1 dk dt is equal to, and here's where things get a little challenging. Notice here that the mass and volume are being multiplied, and I don't have a constant mass. Sorry, that's mass and velocity. I don't have a constant mass. I don't have a constant velocity. Those are both changing, so I can't replace one of those values. I'm going to have to use the chain rule here. Okay, so it's going to be the derivative of the first. That's 1/2 times m, which is just going to be 1/2. Derivative of the inside function with respect to t, that's dm dt, times my value of v squared. And product rule says I'm going to add the derivative of the second, that's 2v, times the derivative of the inside function with respect to t, which is going to be dv dt, times the first, which is 1/2 m. Okay, a lot of simplifying here I can do. In this case, 2 times 1/2 is 1, so I'm just going to have mv times dv dt plus I'll write this as 1/2 v squared dm dt equals dk dt. And depending on what the problem asks, you can do different things here. I can actually do a straight substitution into the equation now. In this case, I am looking for dv dt. So I could just substitute in for everything here. I know that dk dt is equal to 100,000. I know that the velocity is equal to 10. That's going to be 10 squared. I know that dm dt is equal to 20. I'm given a mass of 5,000. I'm given a velocity of 10. And I'm looking for dv dt. And that's the only value that I haven't filled in. Okay? It is possible that you could have to solve for dv dt and write this in terms of the variables first. So you can set this up various ways. Oh, by the way, one thing that I did not take into account here, and I really need to do this, the mass is decreasing at 20 kilograms per second. Decreasing, that is a negative value there. So down here, when I substitute in that rate of mass change, that needs to be a negative 20, and that's being multiplied there. So be careful with that. Anyway, this is 1/2 times 10 times negative 20 plus 5,000 times 10 times dv dt. I can do a little simplifying here. Get 100,000 equal to negative 100 plus 50,000 dv dt. Add 100 to both sides. So 100,000 100 is equal to 50,000 dv dt. Divide both sides by 50,000. And it looks like in this case dv dt is going to end up equaling, I can cancel some zeros here, it's going to be 1,001 over 500, and that's going to be approximately 2.002. Now that's a change in velocity over time. Change in velocity, that's actually an acceleration. So that is going to be kilometers per second squared. And that is the rate of change of the velocity when the mass is 5,000 kilograms and it's traveling at 10 kilometers per second.